Hello, this is Y, and today I'm going to do another tutorial on how to design a counter. A counter is a frequently taught component in digital logic as well, and it is very important and is basically implemented in every hardware and software you may encounter in today's life. What you're going to know before we start on the tutorial on how to design a counter is that you need to at least learn the working principle of flip-flops, and you need to know the working principle of logic gates. And this is going to be split into 4 parts, in which the basic working principle of a counter, a synchronous counter, an asynchronous counter, and a counter but it is limited to some numbers. Let's say it is limited to counting from 0 to 49, and that is called a mod 50 counter. A mod 50 counter resets to all 0 upon reaching the counting sequence of 50. Of course, the 50 is expressed in binary form. And now the first part, counter. A counter is a circuit that outputs its counting sequence, usually ascending but can also be descending. It can be synchronous or asynchronous, depending on the design of your circuit. It could also be implemented in using different flip-flops, like T flip-flop, like D flip-flop, and I will explain their combinations in later part. Let us start with how will a T flip-flop work. We know that T flip-flop is also called a toggle flip-flop. It basically works as its name implies. When the T input is 1, the result toggles. And when the T input is 0, the result here is kept unchanged. Alright, let's have a output table here. Qn represents the initial state of this Q output, and Qn plus 1 represents the state of the Q output when it's influenced by the T input. Let's say we have 0, 0, 1, 1, right? And then we have here, and we know that when T input is 0, the Q is kept unchanged. So the output is kept unchanged in these 2 rows. And when T is 1, the Q output is toggled. Toggled meaning when it's 0, it goes to 1. When it's 1, it goes to 0. So it changes state. Why is T flip-flop important? Because this is basically its working principle adheres to what our counter will be. The counter, when it's outputting the number in binary form, each of the output will be in either 0 or 1, and there will always be toggling between these 2 numbers, right? So let us move forward. A key characteristic of this T flip-flop is that it changes state only when T input is high, and this allows it to alter other flip-flop which is with its own output. What does it mean? It means that when you are combining flip-flop in this connection, actually you can combine them in a lot of different connections. This is just one type of them. And you see that this T is under a constant high input, and the clock is going up and down. And a flip-flop is edge triggered, meaning that the flip-flop will change its output state when the clock is either on a positive edge, also called a leading edge, or a falling edge. Depends. If it is a positive going transition, it is this. If it's a negative going transition, it is this. So in this simulation, I'm going for a positive going transition flip-flop. And now you can see when it rises, its output state changes. And when it's dropped, nothing happens. And when it rises again, it toggles again. And this here, we call it toggle. Both of these places, this as well, this and this, and they all happen at rising edge of the clock input. And you can see in this specific connection, the second flip-flop is only toggled when the first flip-flop is giving it a high input, right? So for Q2 to be outputting high, we need Q1 to be high. So you can see that at this clock pulse, this Q1 here, this region here is 0. So our Q2 is not affected. But in this clock pulse, you can see that the Q1 here, it is already high. So it will toggle. And we can see that it is low when this positive edge comes. So it will keep unchanged, right? And then it is high here, and a positive edge came, and it will toggle. Q2 represents the output of this here, and Q3 represents the output of this. So it works like this. Now have you noticed a very interesting thing? That let's say this is all happening in 1 second, and we have 1, 2, 3, 4, 5. We have 5 periods here. Let's say this is all in 1 second, and we have 5 periods on this clock, and we have 1, 2 and a half. So that's 2.5 Hertz, and we have only 5/4 Hertz here and 5/8 Hertz here. What does this imply? This implies that the changing frequency halves for every flip-flop. Now, what this implies? This is very close to the counting sequence of a binary number, you see. Let's say it is in an arrangement of Q3, Q2 and Q1. You can see that it's 0, 0, 0 here. The clock pulse arrives, it toggles, and then nothing happened on here, and then something happened here, positive edge. It toggles again, changes, it changes, it changes, and go on and on. And what is this? This is basically the counting sequence of a binary number. And you can see as well how the binary number, their changing frequency differs, right? Basically, if you let this to start off at 32 Hz, the second one will change at 16 Hz, right? And so on. Alright, this is basically the counting sequence first. Now I will go into a synchronous counter. A synchronous counter meaning that all the flip-flops inside will use a common clock. What is this common clock? This common clock is controlling the clock input of all of the flip-flops in this circuit. You can see here, 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 and here, right? Alright, and now let's go on. Alright, let's start to understand what this circuit is doing here. We know that in a binary counting sequence, this here toggles every clock pulse, every positive going clock pulse, right? It toggles every positive going clock pulse, and this one, it toggles only when this one is high. You see, it toggles only when this one is high. it toggles only when this one is high, and it toggles only when this one is high, right? And further observe, we can see that this one, it toggles only when both are high, and it toggles only when both are high. So how do you ensure that it toggles only when both of them are high? You take the output of these two and connect to the input of the 2 power 2 place. You can see that the output of the first flip-flop is here, and the output of the second flip-flop is here, and connect through an AND gate, and this AND gate is connected to the input of the third flip-flop. And in this way, the third flip-flop will only toggle when both of these flip-flops are high. And the same applies to any coming post flip-flops. Like you see, the output of the AND gate is taken here, and the third flip-flop output is taken here. So this is basically 1 and 2 and 3, right? And it is connected to the input of the fourth flip-flop, right? So now you can count from 0, 0, 0 to 15 on a 4 gate. If there's only 3 flip-flops, you can only count from 0 to 7, and then we'll go to 0 again. And that's for asynchronous counter. And part 3 is an asynchronous counter. An asynchronous counter is a counter where the flip-flop is not connected to a common clock. Usually, in a common case, the clock of the next flip-flop is controlled by the output of the previous flip-flop, either the complement of the output here, or using just simply the output. You can use both. When we are using the complement of the output instead of Q, let's say when we are using Q0 instead of Q, what happens is that this counter will count from 0000 to 0001 all the way to 1111, then back to 0000. Because in this setup, the second flip-flop is only going to change, the second flip-flop is changing half the frequency of the first flip-flop, right? And when this is high, this is low, and when it toggles again, this will become high, and this become low. But when it toggles again, when it becomes high, due to this being low, it's kept unchanged, right? So that it follows a binary counting sequence, and it applies across all 4 flip-flops. So you can see the counting sequence is here, and continued here, and here it repeats again, right? But in this D flip-flop case, if you are controlling the flip-flops using the Q output, in the first tick, all of these components will instantly go to 1. Why? Because you can see that if this goes to 1, this is 1, the first input is 1, the Q will go to 1, right? And then this clock will be influenced and it will go to 1. And since this is also 1, this will go to 1 also. And it propagates further all the way to the last flip-flop, and all will become 1. And then when the next positive going transition arrives, this here will become 0. Why? Because if it is already 1, Q0 will be 0. Then its input will be 0. What happens if its input will be 0? It will change to being 0. And this is a descending asynchronous counter. You can see its counting sequence is descending. Now you may be confused. Let me just take a note here. This is the 2 to the power of 0 place, and this I'm writing in reversed, like how we usually write a binary number. So 2 to the power 0 is actually here, this place. You can see that it's counting descending, and this is how you basically, in an asynchronous counter, how do you adjust it to be counting ascending or descending. The next thing, will you choose asynchronous or synchronous? Well, if it's an assignment you are doing, it depends on what your lecturer asks, but both of them have their own merits. An asynchronous counter is easier in design, but it works at a lower frequency. Let's say if each of your gates have 10 nanoseconds of propagation delay, it means that the moment it accepts the positive going clock pulse to the moment that it outputs changes, the time delay in between is 10 nanoseconds. And in an asynchronous counter, just as we say above, you see that it propagates, right? The second flip-flop, it can only change when the first flip-flop has done its part, and the third, it can only change when the second has done its part. So the total delay of this asynchronous counter will be the sum of the propagation delay of all the flip-flops inside the counter. But if it is synchronous, you don't have to consider about the delay. The delay will only be one of the counters. That means no matter how many flip-flops you have in your synchronous counter, the delay is only one flip-flop. Alright, but synchronous counter has its demerits. It is usually harder to design. You will see in later examples. Now I'm going to show you why does this happens. How is the frequency of the synchronous counter is higher than an asynchronous one. Alright, here we have Logisim again, and this is the above one is an asynchronous and the below one is asynchronous. You can see that the design is slightly different, right? Slightly more complicated. Alright, let us see. First, you want to close the simulation enable so that you can observe how many tick it takes for the signal to complete. At the start of the counting sequence, when the change only influences the first flip-flop, both are the same. They usually don't have difference. So you want to tick it once. You want to observe first, 2, 3, 4, 5. Right, so they are both done in 5 steps, and the record is complete. Both are turned to 1. Alright, so let us observe if the influence is not just the first flip-flop but the last flip-flop. So let me just adjust it pretty quickly here. Alright, okay, now we want to close the simulation. Alright, let it go on a positive going transition and count 1, 2, 3, 4, 5, 6, 7, and we can see in the 7th tick the below has already complete, and 8, 9, 10, 11, and 11. So 7 ticks for the synchronous counter and 11 ticks for the asynchronous counter. and this difference increases the more flip-flop you add, meaning the bigger your number, you want to count your number, the lower the frequency of the counter will be able to operate at, because it will gradually increase in difference. And this is what I mean when I say the max operational frequency is different. Because if you take more time in one single step of counting, the total step of counting in a fixed amount of time you can do is basically cut by a lot. So if you aim for speed and efficiency, you want to go for the synchronous one. But if you aim for simplicity and cost cutting, you want to go for the asynchronous one. Alright, so this will be all the content of this part of the video. The next part of mod n counter will be explained in the next video. Thank you very much.